Okay, so the question here is, what is the derivative of the inverse sine? Okay, so notice over here we have the graph of both the sine function, shown here in red, and I've only graphed it up to pi over 2. And in purple we have the graph of the inverse sine. And of course, as long as we have restricted the domain of sine of x to stop at pi over 2, and if I were to show the left-hand side of this graph to stop over here at negative pi over 2, then this red curve and this purple curve have a certain symmetry to them. Namely, if we were to draw in this line right here, this line y equals x, then these two curves would be symmetric to one another about this line. Now, what is the derivative of the inverse sine? Well, remember, graphically, we're talking about the slope of a tangent line to this purple curve here, to the curve given by y equals inverse sine of x. So let me go ahead and pick some x value here to consider. Let's say we pick this point right here. And let's see, if we find the corresponding point on the graph, maybe right here, we should be able to draw in a tangent line to the curve. So let's go ahead and draw that. There we go. And let's also get an idea of how high this point is. How high should this be if our input is simply x? Well, the height's given by the y coordinate, and so the height right here of this point should be the inverse sine of x. Now, we know, given the symmetry here between inverse functions, that there must be a mirror image of this purple tangent line over here tangent to the red curve. And we can find the corresponding point of tangent C on the red curve just by looking at the x and y coordinates of this purple point and swapping them. So there should be some point, probably right about here, which is located where? Well, let's see. Its x-coordinate should be the purple point's y-coordinate. So this will have to be the inverse sine of x. And the height of this point would then be x. Again, we just reversed those two purple coordinates. Okay? And just like we mentioned then, there should be a red tangent line through this point that is a mirror image of this purple tangent line. So let's draw that. Okay, there we go. Now, does it make sense that this purple slope and this red slope should be reciprocals of one another? Think about what slope is. It's a rise over a run, and the run here translates into a rise here, and the rise of this line would translate into a run in this line. So rise over run becomes run over rise, and of course all you're doing there is reciprocating your slope. Now, what does that have to do with the derivative? Remember, we're after the derivative of the inverse sine of x that should give us a slope of a tangent line to y equals inverse sine of x at x. So we are after this purple slope. Let's call this purple slope m, a purple m. Okay, so whenever we write purple m, we mean the slope of this particular purple tangent line where the input value here is x. And in a like manner, let's refer to the slope of this red tangent as red m. Okay, so we have this right here. Now, going back to the derivative, this means that the derivative of the inverse sine of x is purple m, and that in turn, given the reciprocal relationship between the slopes, given that they're symmetric about this y equals x line, and these points are obtained by these points just by swapping the x and y coordinates, that means that purple m is equal to 1 over the red m, the reciprocal of the red slope. Now, why would I do this? Why would I rewrite a purple slope as a reciprocal of a red slope? Well, we know something about the slope of tangent lines to this red curve. This is the curve y equals sine of x. The slopes of tangent lines to y equals sine of x is given by the derivative of sine of x. In other words, these red slopes are given by the cosine of x. So for example, if I want to know what is the slope at 1, well, that would be the cosine of 1. If I want to know what is the slope right here at the end point, that's pi over 2, of course, in terms of an input value, that would be the cosine of pi over 2. If I want to know the slope at this point, where the input is this, then it would be cosine of this. So this red M is the cosine of this input. Let's write that down. Okay, so there we go. Now, you may have seen problems in the past where you had to take a composition like we have here of two trig functions, one of which involved a inverse trig function. Look, this inverse sine of x is an angle. It is the angle whose sine value is x. Let's call that theta. Okay, so this right here is an angle. Now, it's an angle whose sine is x. Suppose this angle, for the sake of argument, was between 0 and pi over 2 radians, or between 0 and 90 degrees. Then it could be an angle of a right triangle, right? For example, this angle right here. Notice I've labeled the opposite side as x units in length, the hypotenuse as 1, and so then opposite over hypotenuse would give you a ratio of x over 1, or simply x. And so the sine of theta, which is opposite over hypotenuse, would then be x, which is what I desire. Okay? Now, in the off chance that this x was a negative value, we could draw a similar sort of picture, just having a negative x here and making sure our signs, that's positive or negative, work out correctly. But this triangle right here will serve to illustrate the point. What is the cosine of this angle? Well, that would be the adjacent length over the hypotenuse. What's the adjacent side length? Well, couldn't we use the Pythagorean theorem to figure that out? Wouldn't this length necessarily be the square root of 1 minus x squared? And here's where that business about, well, what happens if x is positive or what happens if x is negative, where things really don't matter because we're going to end up squaring this x anyways. But now look, cosine of this angle is this over this, or just the square root of 1 minus x squared. So I can rewrite this as this. We have just found the derivative of the inverse sine. It is 1 over the square root of 1 minus x squared. Isn't that nice?